Hi, everybody. A unit vector is a vector that points in the same direction as some vector, but has a length of 1. And this set of problems is about how you can discover how you can find unit vectors. So we know that scaling a vector will change its length, but it won't change the direction. So if we want a vector that's the same direction, but has only unit length, a length of 1, it should be the case that I could just take that vector and scale it by some magic number that will shrink it down until its size is 1. So let's figure out how we could think about what is that magic scale factor. Here I've got a vector 6, 8. Let's find its magnitude. That's its length. So magnitude is going to be the length of the hypotenuse there. So 6 squared is 36. 8 squared is 64. And so that's going to give us square root of 100, which is 10. All right, so we've got that the length of A is 10. Let's imagine what happens if we scale the vector in half. So if we scale it in half, it should look like this. And we'll do that just by multiplying each of the components by 1/2. So 6 times 1/2 becomes 3. 8 times 1/2 becomes 4. In the picture, if this whole thing was A, this part right here is A over 2. And then here's another A over 2, if I wanted to imagine two of them together. Okay, so what's the magnitude of A over 2? Let's work that out. It should be 3 squared is 9. 4 squared is 16. 9 plus 16 is 25. So the length is 5. So let's notice that all of the measurements, if we imagine this as a triangle, all the measurements of the triangle scaled by 1/2. The x component went from 6 to 3, so it halved. The y component went from 8 to 4, so it halved. And the length, the hypotenuse, went from 10 to 5, so it also divided by 2. So I think the big upshot here is that multiplying by a scalar scales the entire triangle. And whatever you're multiplying each of the components by, the length is going to get multiplied by that same amount. So let's do one more. What if we were going to scale the original vector A by 1/10? So we're going to shrink it down to be 1/10 its original length. Really, we don't need to do any math here based on what I just said, because if that 1/10 is affecting all three sides, 6 is going to become 6/10, 8 is going to become 8/10, and then I don't even need to work out, square root of whatever here. I know that the magnitude is also going to scale by 1/10. So 10 divided by 10 gives me 1. So this turns out to be the unit vector for our original vector A. It's right here. It points in the same direction, but its length is only 1. And you see the components are very small, 6/10 over here and then 8/10 there. Okay, so now let's generalize. Why did scaling by 1/10 result in that unit vector? Like, what was special about 1/10? Well, 1/10 was the length of the original vector. And it sort of makes sense that if I'm looking to scale a triangle down so that its length here is 1, I should use as a scale factor whatever the original length was. If the original length was 22, I should divide everything by 22. If the original length was root 105, I should scale everything down by root 105. So here's the general theory. So that was our general theory. Scale it down by its own length. In other words, let's divide by its own length. So let's test that theory now with 5, 12. All right, so here we've got vector v. I want to make it into a unit vector, so length 1. The magnitude of v is going to be 12 squared plus 5 squared, which is 144 plus 25, which is the square root of 169. Maybe this feels familiar to you and you think, oh, I know how that simplifies, and maybe not. Let's not simplify it now. Let's just keep it this way. So how are we going to modify v? Let's take v, but let's multiply it by its own length. So let's multiply it on the outside by 1 over root 169. What's that going to give us? That's going to give us 5 over root 169 and 12 over root 169. And what we know is that that should end up being length 1. Let's just go ahead and test to verify that it is. So root 169 is actually just 13. So here we've got 5 over 13 and then 12 over 13. If we're going to go ahead and compute the magnitude of that, remember we're expecting it to be 1, because doing that division should have scaled it down to be length 1. If I am going to do all of the number crunching, I've got 5/13 squared and 12/13 squared. What's that going to end up being? Here I've got 25 over 169, and 12 squared is 144 over 169. And you know that 144 plus 25 is 169. So I've got 169 over 169. So that's 1. So here I've got root 1, which is 1. So we've confirmed that it worked. We don't need it to ever confirm that it works again, because we thought about it carefully, and we know that it should work. So let's go ahead and write this in a form that we can take away. If I've got any vector v, the way that you can find the unit vector is what I'd written here, except let's do it in general. So I know that if I multiply on the outside by 1 over v's magnitude, that will be the unit vector. A different way of writing this is, instead of multiplying by 1 over the magnitude, you could think about it just as, let's divide v by its own magnitude. And this is a common way of writing the unit vector as well.